Okay, Matt Roscoe here at the University of Montana, section 4.2 on inflection points in our course Calculus for Middle School Teachers. I want to go back to our working example and talk a little bit about what we can learn from locations on a graph where the second derivative is equal to 0, and then review about what derivatives tell us, in particular what the second derivative tells us, and then formalize how we can find points of inflection, and then go ahead and do that on several examples. So let's talk a little bit about what the first and second derivatives tell us about this function. So we already have investigated what the first derivative tells us about the function. Let's investigate a little more fully what the second derivative tells us, and in particular, how do we find or determine where a function has a point of inflection. So let's go ahead and carry that out now. So our function at hand is f of x equals 4x to the third minus x to the fourth. Okay, so if we take the first derivative of that function, we get 12x squared minus 4x to the third, and if we take the second derivative of that function, we get 24x minus 12x squared. So what we're really interested in this chapter is what does the second derivative tell us when it is equal to 0? So in particular, when f double prime is equal to 0, what does it tell us? And you should be able to kind of think about this, right? That when the second derivative is equal to 0, then we have some sort of a thing going on there where there is no concavity. It's neither positive nor negative. So it might be one of what we call these things that we call inflection points, or locations where we change in concavity from concave down to concave up. So I will just write next to this potential inflection point. Okay, so that's how you find your potential inflection points. That's just like in the first derivative, when you set it equal to 0, you find these things we call critical points, which are potential local maximums and minimums, but not always. So they are the candidates, or potential inflection points. Okay, so if we set the second derivative equal to 0, that's 24x minus 12x squared. We can solve that pretty quickly. I'll factor a 12x out of the binomial, and what do I get? I get 2 minus x equal to 0. So applying the zero product property, we can see that either x is equal to 0 or x is equal to 2 in order for the product to be equal to 0. So now we have two potential inflection points. Okay, so these guys are our potential inflection points. I'll just box them. And how do we tell if they really are inflection points? Well, you should think to yourself, if as I'm approaching 0 from below and I transition from, say, a negative curvature to a positive curvature, or a concave down graph to a concave up graph, then I've definitely got an inflection point. And the same would be true at 2. If I transition from from positive to negative, or negative to positive valued second derivative, then I must have a spot there where the curvature is changing from concave down to concave up, or vice versa. So we'll evaluate it just that way. We'll kind of think about, well, what's happening to the left of 0, in between 0 and 2, and to the right of 2. So if I put a negative number in the second derivative, I get, let's say, -1 as my test point. I'll put a -1 in there. I get 24 times a -1. That's a -24. Minus 12 times -1 squared, so that would be minus 12. So -36. We're definitely a negative valued second derivative to the left of 0. Now, since at 0 the second derivative is equal to 0, we know that there are no other locations in here where we transition, so where we move through 0. And since this is a continuous function, this polynomial that represents the second derivative, we can assume that everything to the left of 0 has a negatively valued second derivative. Let's see what's happening between 0 and 2. A good point to pick might be 1. So if I pick 1 and put it in there, I get 24 times 1 minus 12 times 1 squared. So I definitely have something that's positive in there. And since I'm only valued at 0 when x is equal to 0 or 2, then I would assume that everything in between 0 and 2 would be positively valued in the second derivative. Okay, so we definitely have a point of inflection at x equals 0. This one is confirmed as a point of inflection because we went from negative curvature to positive curvature, so it is an inflection point. Let's see if the same thing is true at 2. What would have to happen at 2 for it to be an inflection point is this would have to be a negatively curved or concave down graph to the right of 2. So let's go ahead and check that. Let's put a nice number to check would be 3. So if I put 3 in there, 24 times 3 minus 12 times 3 squared. Let's just see what happens there. 24 times 3 minus 12 times 3 squared. I get negative 36, so it's a negatively valued second derivative there. So again, 2 is an inflection point because we went from a concave up graph to a concave down graph as we transition across 2. So what can we conclude? We can conclude, therefore, that x equals 2 and x equals 0, 0 and 2, are inflection points on the graph of f. All right, so that's what second derivatives tell us about I guess about the shape of the graph. Let's go ahead and just look at the graph really quickly. Maybe I'll put it over here so we can look at it next to the work. We found that at x equals 0 and x equals 2, we should expect an inflection point. Those are the spots where the second derivative is equal to 0. They are highlighted in blue here, and you can see that indeed those are the spots where we kind of roughly guess that the curvature is changing from one value, or I guess one from positive to negative or negative to positive. So let's go ahead and see where the curvature is positive. It's positive in between. That's where the second derivative is positively valued, and it's negative on either sides of 0 and 2. So indeed, the two blue points would have to be inflection points because that is where the graph of the function is transitioning from concave down to concave up, and then from concave up to concave down. And those are the only ones on the graph of this function. So there will be no other inflection points as we move out the legs of the graph towards positive or negative infinity. And there are no others that are in this domain in which we are viewing the graph. So some nice stuff that the second derivative tells us. One thing that might be worth pointing out is that these spots where the inflection changes is where, an increasing function, you can kind of see this happening. If we sort of think here, we're increasing at a certain rate. We're still positively valued, but now we are decreasing. Okay, so what it does is it's sort of like a turnaround point where the function has a radical change in the rate at which it's increasing or decreasing. Let's go ahead and leave it there and let you think about that more in your homework problems. Let's go to a large screen. So what do the first and second derivatives tell us about a function? Well, remember the first derivative tells us when it is increasing or decreasing. If it's positive, it's increasing on an interval. Negative, it's decreasing. And the second derivative tells us about concavity. If it's positive on an interval, it's concave up on that interval. If it's negative on an interval, it's concave down. So if we call a point P in the domain of F where the graph of f of x changes concavity an inflection point, then we can find those inflection points like we did in the opening example. We can first find the spots where the second derivative is equal to 0. Well, it turns out that it's not just that. It's also spots where the second derivative is undefined as well. But those are the potential inflection points. And if the second derivative changes sign to the left and to the right of that inflection point candidate, then P is an inflection point. So you have to do sort of this two-step analysis. First find where the second derivative is equal to 0 or undefined, and then evaluate whether or not it's changing sign at that point. And if that's the case, then we have an inflection point. So let's take a look at some examples here. Get that back. Well, come back here, you. Let's see. There we go. Let's take a look at a few of these examples that we looked at in 4.1 and see if we can analyze them for inflection points. So let's do the first one. This is f of x is equal to x minus 2 natural log of x. Well, we found that this guy has a derivative of 1 minus 2 times 1 over x. And so probably easier to write this 1 minus 2x to the negative 1. Getting ahead of myself there. Because then we can easily calculate the second derivative. The derivative of 1 is just 0. So we have 0 minus 2 times, let's say the derivative of x to the negative 1 will be negative 1 x to the negative 2. So the second derivative written more compactly is 2x to the negative 2. That's the same thing as 2 over x squared. So I can see that the second derivative equal to 0 will be where our potential inflection points are. So if I set 2 over x squared equal to 0, I can see that that will never happen, right? Because no matter what I do for x squared, I can't make 2 divided by something equal to 0, right? So no matter what I plug in for x squared, there's no solution here. So there's no solution here. But what about this other kind of not often overlooked one? What about where it's undefined? And I can see that 2 over x squared equal to 0 is undefined when, is undefined when x is equal to 0, right? Because 2 divided by 0 is undefined. So this is a potential inflection point, but a quick look back at the function, and maybe I should have done this to begin with, I can see that the domain of this function is restricted. Because the natural log is part of this function, the natural log is restricted to positive real numbers only. X equals 0 is outside of the domain, so it's not an inflection point candidate because it's not a point on the graph. So what can we say? So if there is no solution here and the one undefined point in the second derivative is not part of the domain of the function, then what that means is that there are no inflection points on this graph. So what that means is that the graph is either all concave up or all concave down. And a quick evaluation of the second derivative here, if we think 2 over x squared, and the domain is positive reals, if I put any positive number in there, I get a positively valued second derivative. So the graph must be concave up for x greater than 0, the domain of the function. So let's take a quick look at it just to make sure that we are indeed correct. So what do we have? We have x minus 2 times the natural log of x. And we'll go ahead and hit well, zoom 6. Let's just say we're getting an initial view. I can see the graph. Yep, indeed, something that looks concave up. It is restricted in domain from 0 to infinity, it looks like. So I'll get a better window here. Let's just do 0 to 10, and then it looked like it was always positive in value. So yeah, indeed, it looks like we have a concave up graph everywhere, and our inflection points are non-existent here. Okay, so kind of a tricky place to start, but some graphs do have no inflection points, right? It's possible. Let's go ahead and move on to the second example. What if g of x was equal to x to the 5th minus 5x? Well, then g prime of x is going to be 5x to the 4th minus 5, and g double prime of x is going to be equal to, let's see, 20x to the 3rd. Okay, so where is g double prime of x equal to 0? Well, that's where 20x to the 3rd is going to be equal to 0, which only happens when x is equal to 0. Okay, so we have a potential inflection point, and so let's check it. So really we know that the graph can only transition from either positive to negative or negative to positive when x is equal to 0. So let's try and find out what's going on to the left and to the right of 0. So what if I put a negative 1 into the second derivative? Here's the second derivative. If I put a -1 in there, I can see it's going to be negatively valued because a negative cubed is still negative. And if I put a +1 in there, I can see it'll be positively valued. So it's positive to the right of 0. So we transition from concave down to concave up at 0. So that means 0 is an inflection point. So let's see, how do we write that? You can either write x equals 0, or the point, in this case, 0. If I put 0 into the function itself, I get 0 out. So it must go through the origin. So either x equals 0 or the point 0, 0 is an inflection point of f. Okay, so let's take a look at that one on our graphing calculator. X raised to the 5th minus 5x. Let's just do a zoom 6 and see what we get. Okay, something that looks like that. Pretty narrow view, so I think I'm going to restrict the domain from -2 to 2 and graph it again just to get a better picture. Okay, now I can definitely see I can see something happening here where the graph is concave down, and then I can see something happening here where the graph is concave up, and that seems to correspond nicely to what we found before, that 0 or 0, 0 is indeed an inflection point of the graph. All right, better clean that screen up. Got it. And let's move on to the last one. So what if we had 5x times e to the negative x? We're calling this one h of x, right? 5x times e to the negative x. Well, h prime of x, as we saw before, we have to use the product rule because we have x times e to the x. 5 out in front. It'll be first times the derivative of the second. That's x times e to the negative x times the derivative of negative x, which is -1, plus the second times the derivative of the first. That'll just be e to the negative x. Okay, so we get 5x. Well, I guess it would be a -5x, right? -5x e to the negative x plus e to the negative x. Okay, well, so this is kind of an interesting one because we get a piece of the function in the first derivative that's equal to the function itself. So we can easily take the derivative of this one by just attaching a negative to the derivative that we just got out, right? So the derivative of this one will just be the negative of the first derivative. So it'll just be 5x e to the negative x minus e to the negative x. So this is, h double prime of x. So that's the derivative of the red part above. And then if I kind of look at the derivative of e to the negative x, I can take its derivative by just thinking of the chain rule. It would be the derivative of e to the negative x, which is just e to the negative x, times the derivative of negative x, which is just a -1. Okay, so it appears that I have a negative e to the negative x, a negative e to the negative x, so our derivative is 5x e to the negative x minus 2e to the negative x. Okay, so that's our second derivative. Okay. Let's see here. Oh, I made a mistake. I can see where I made it. I forgot to distribute the 5 right here. I notice now, right? Does everybody see that? Okay, so if I take that mistake into account, sorry, good thing I did some notes. I put a 5 there. And let's see. This is going to be, have a 5 in front of it as well then. My fault, small mistake there. I'll leave it in the video just so you realize I am not faultless. So it does look like it's 5x e to the negative x minus 10 e to the negative x. Okay, now I feel a little bit better. Let's go ahead and find out where the second derivative is equal to 0. So that's going to be equal to 0 at 5x e to the negative x minus 10 e to the negative x is equal to 0. I can see I have an e to the negative x and a 5 common to both, so I'll take that out. 5 e to the negative x, that all times, let's see, it'll be x minus 2 equal to 0. Okay, so we have a zero product property here going on. So either this is equal to 0, 5e to the negative x is equal to 0, or x minus 2 is equal to 0. This one's easily solvable to 2. But this one, you'll have to think about a little bit. E to the negative x, that's a negative decay function, right? And it never ever reaches 0, right? The exponential function gets infinitely close to 0, but never quite reaches it, so there's no solution here. So that doesn't ever happen. Another way you could do this would be, of course, well, anyway, no solution on that side, x equals 2 on this side. Okay, so let's see if I can get those both on the same screen. Okay, so the question is, what's going on at x equals 2? Here is 2, and what is the second derivative doing? F double prime of x before and after 2. So what I'll do is I'll pick the test point 1, and I'll pick the test point 3 and ask what's going on there. So if I put a 1 into the second derivative over here, that would be the same thing as 5 times 1. So it would be 5 times e to the negative 1 minus 10 times e to the negative 1. And when I run that through my calculator, and sometimes you just have to do this, I get a negative value there. So this is negative on this side. Let's take a look at what happens when I change that to 3. And we'll see what happens there. And there I get a negative value as well. Let's see. Oh, I see what I did wrong. I actually want to, I got to be a little bit more careful. If I want to put a 3 into here, it'd be 5 times 3 instead of 5 in my argument. I should have 15 there, right? 5 times 3 minus 10, there it is. So I'll put insert 15 and hit enter. There we go. I got a positive the first time I ran it and a positive again there. So it does appear that we go from concave down to concave up at the point 2 on this particular graph, x equals 2. So what can we conclude? We can conclude that at the point 2, x equals 2 is an inflection point of the graph. If I wanted to put, I could put 2 into the function and find out what its y-coordinate would be, but let's go ahead and just trace the function and see if it does indeed seem to have that behavior at x equals 2. So it'd be 5x times e raised to the negative x, and I want to just hit a zoom 6 just to get a sense of what this thing looks like. Okay, it looks like a lot of action happening around the origin there, so I'll change my window a bit. How about negative 2 to 2, and I don't know, negative 5 up to 4 on the y. Oh, except for that's not going to help much because we think the inflection is actually at 2. So let's go to the window again and make the x max 4 instead of 2. Okay, now we should be able to see it. So apparently what's going on is, here's my value of 2. We would be concave down up until about right there, and then concave up on the graph from there on out. And so it does appear, yeah, that the graph is transitioning at that location. X equals 2 is analytically the inflection point. Okay, well, I hope that that gives you some sense of what's going on in the inflection point chapter, and I look forward to hearing your questions. and good luck on your homework.